Okay, so for queries in the relational algebra, we can design sometimes can be very complicated and can also be very known, right? Before we show you how to represent the natural join, I mean, this representation can be very known, right? I mean, the expression of the query. And sometimes we can even have a longer expression than this. Then how to represent it will be a problem. So normally we can borrow the ideas we learn from other algebra, right? I think you have learned this in the elementary algebra, right? About the product as well as plus minus of two numbers or some numbers. And we can represent an expression in multiple ways. And so algebra always allows us to express the sequence of operations in a natural way, right? Now for in elementary algebra, we can represent an expression in this way. We calculate the x plus 4 parentheses times parentheses y minus 3. I think you know what does this mean, right? It means we calculate the x plus 4 first, and then y minus 3 second, and further times the result together, right? This is what this expression means in the elementary algebra. And it will be very similar for the relational algebra. They also allow us to write down some expressions in a very similar way. And before we talk about the relational algebra, we can provide you with some other representations. We can represent the same expression in the elementary algebra. So x plus 4 times y minus 3. Besides this one, do we have any other ways to represent it? We can also represent this same expression by using a sequence of assignment statements, right? Or we can write down just in a similar way by using an expression with several operators in the same expression, right? Or we can use a tree to represent the same expression. I think you have learned this in the discrete mathematics, right? So what does this mean? We can represent the expression, right? We can say it is an expression. We have x plus 4 times y minus 3, right? This is the expression we want to represent. We can represent it in three ways. The first one we can represent as a sequence of assignments, right? We can represent it as a sequence of assignment statements. What does this mean? So we can represent it as, for example, we have S1 equals to what? X plus 4, right? This is the first assignment we can represent. We have S2 equals to y minus 3, right? And we have S3 equals to S1 times S2, right? Then this S3 will be the same as this expression we show here, right? This is the first way we can represent it. Besides this, we can also represent it as an expression with multiple operators, right? It will be the same as the one we show here. Right? Okay, this is the second way. The third way we can represent it will be using a tree, right? I hope you learned this from discrete mathematics. What does this mean? We can represent it as a tree, right? We can, for example, we can choose some diagrams here. It is different. We can change the format and the color with white with some line and the boundary, right? We use a light boundary. And we can represent it as a tree. The tree will have a bunch of nodes and leaves, right? So, for example, we have a tree. The first operator we have will be the product. Let me go to text so we can change the color to black. This tree have some branches, right? The left branch will be another operator, right? And it have a right branch. Left branch will be represented as expression, like with this plus as operator, right? and the right branch will be expression with minus as operator. And below them, we even have this x as a number, right? It works on. And then we have 4, right? It will be similar for the right branch. We have this y and 3, right? Right. So we can represent the expression as a tree as well. We can make it different. We can remove the boundary we remove the boundary for the numbers, right? So for operators, we have this boundary, right? For the numbers, we don't have boundaries. It will be a tree. We can further add the links among the nodes. Right? So this plus operator connects to both x and 4. It denotes x plus 4, right? It will be similar for the right hand side. We have minus, we have y minus 3, right? And we can represent it as by connecting y and 3 with this minus operator. And further between them, we have this plus and minus connected to the times, right? We can connect them together as shown here. So this is another way to express the same expression by using the tree structure. Okay, so this is about the elementary algebra. It will be very similar for the relational algebra. And let's go back to the slides. So given an expression in the relational algebra, we can also represent it either as a sequence of assignments, or an expression with multiple operators, or as an expression tree. And we can show you how to do this. The first way is to represent as a sequence of assignments. We can create some temporary relation names, and also renaming can be used by giving the relation a list of attributes. And we can provide you with the example for defining the theta join, right, between two relations. We want to calculate the theta join between R1 and R2. According to the definition of theta join, we can represent the operator as we define the R4 as a temporary relation first. It denotes the product between R1 and R2, right? And then we can further do the select with C as a condition on this R4, this temporary relation, right, to get the R3 as the result. So this is the same expression as the theta join we define here by using a sequence of assignments. And we can also define the theta join by using the select with condition C on the R1 times R2 directly. In other words, we can represent the theta join by using an expression with multiple operators, as shown here. It is the same as the one we showed before, but this one we just use one expression, but with multiple operators. For this expression with only one row, but with multiple operators, then we need to know how to calculate it. We also need to know the precedence of the operators, right? Generally, among all the operations we showed before, we first calculate the unary operators, like select, project, rename. They have the highest priority in the expression to calculate. And then we calculate the product as well as joins, and then the intersection, and finally we calculate the union and set difference as the operations. It will be similar, right? For the elementary algebra, we calculate the product first, and next we have the branches, right? Then we calculate the minus or plus, and etc. So you need to know the priority among all the operators to be calculated in the expression. And you can always use the parentheses to force the order you desire. If you want to calculate one first, and then you can use the parentheses to highlight it, we need to calculate this one first before the remaining ones, right? Okay, this is the expression with several operators. We can also represent it as the expression tree by using these operators as nodes as well as some relations as nodes, right? It will be very easy to draw a diagram about trees as we showed before. And for the trees, we have the leaves as a branch, and we have the interior nodes as operators. They can be applied to the child or children nodes. We didn't show the operation here because we have a more complex example to show later about how to join a tree to denote our expression. Okay, so this is about expression, and let's try to do an example together.